The topic that we are considering, namely the isotopy of the fundamental space-time symmetry, are truly at the very, very heart of everything that we are doing. So it was mandatory for me, after completing the step-by-step isotopy of the Lorentz and Poincaré symmetry, I had to pass to the step-by-step isotopy of the spinorial covering of the Lorentz-Poincaré symmetry, namely the SL2C multiplied by the translation, again here written in an 11-dimensional form. This was done in great details with a variety of papers, which were mostly written when I was at the Joint Institute for Nuclear Research in Dubna. Here, but first we have to look at the isotopy of SU2. For the Poincaré, Lorentz-Poincaré, we did the isotopy of the rotational symmetry. Here we have to do the isotopy of SU2. Now remember from lecture 2b, the so-called regular representation of the Lie-Santilli isoalgebra are given by simple non-unitary transformation. Namely, you select an arbitrary, regular, non-singular, non-unitary transformation, and that's essentially what you do. You pick up, those are the Pauli matrices, you subject them to a non-unitary transform, and you reach in this way, automatically, the Lie isotopic level. The Lie algebra is mapped into the Lie-Santilli isoalgebra, etc., etc. Here the way it is simply constructed. We assume an Euclid-Santilli two-dimensional space, and of course you impose that to be SU, the determinant has to be 1. And then you select a non-unitary transformation, and you subject the Pauli matrices to this type of very simple transform. I have two cases, and a diagonal non-unitary transform and non-diagonal non-unitary transform. However, as also indicated in lecture 2a and 2b, when you use the simple construction of Lie-Santilli isotheory, then the eigenvalue, the structure constant, remains constant and actually are not changed. So conclusion, despite the enlargement of the algebra, the eigenvalue at the isotopic level of the isotopic SU2 are the conventional one, namely Pauli matrices still represent a particle with a conventional spin 1/2. At that moment, of course, the usual criticism, they are very anxious to jump, oh, but this is trivial, this is very trivial non-unitary transformation, this is nonsense, has no value. Well, I would like to guard the colleagues in good faith and to fend off this type of attempts to control the mind, opposing structural advances, because despite the simplicity, which is not denied, the implications are very big, and we will see them. In fact, this is an explicit and concrete realization of the hidden variable in the very heart of particle physics, spin 1/2. Because from this unitarity condition, then N1 and N2 have to be one the inverse of the other, and they can be interpreted as the hidden variable. So you will see a number of basically new application, by far non-trivial. However, the Lie-Santilli isotheory also admits the irregular representation, and those are no longer reachable by a trivial non-unitary transform. It is at that moment where you see the implications in all their light. Indeed, here is, for instance, one among many examples I worked out when I was in Dubna. Also, this other article I wrote when I was visiting the unforgettable Professor Jacques Lomos at the Estonia Academy of Science. And here you see an arbitrary function in the diagonal part. The structure, you see now the emergence of structure functions, and you look at the eigenvalue, and now the spin becomes a local variable. I repeat, the third component of the Pauli-Santilli isometrics characterize a plus or minus, but is an f of r, a locally varying quantity. And the same for the magnitude of. We are talking about this is the possibility of representing the spin of an electron when in the core of a star or inside a black hole cannot be spin 1/2. The same as when the electron is isolated in vacuum, rotating around the proton in the structure of the hydrogen atom. Ladies and gentlemen, this will be excessively simplistic. We have to admit we do not know, so we work out the theory that the spin becomes variable, and then we either prove it valid or we disprove it with experiment. That is true scientific process without politics. Now, to construct the remaining component of the isotopy of the spinorial covering of the Lorentz-Poincare symmetry, I had to construct the infinite class of all possible isotopy of the Dirac equation. This is a topic that has been discussed by many people. Unfortunately, most of those people, the formulation is not invariant, and this is the reason why I don't want to present it here. But because there are insidious aspects in the correct interpretation. Also, there is a very specific target for this isotopy. The conventional Dirac equation represents the structure of an hydrogen atom. In particular, represents the electron under the external field of the proton. As you know, it represents only one particle. It's not a two-body formulation. Well, what is called the Dirac-Santilli isoequation instead represents the electron when inside the proton, in the synthesis of the neutron, when it experiences all the non forces, non-linear, non-local, and non-potential forces. So that's the aim. And indeed, this equation has indeed permitted the exact numerical and invariant representation not only of the mass, with the mass spectrum that is done in the 20th century, no, of the totality of the characteristics of the neutron when at the end of its synthesis from the hydrogen atom. So this equation has already been proved to have fundamental implications, at least in the line of investigation in which we are interested. Very well, let's see at least in summary the construction of what is today called the Dirac-Santilli isoequations. All the original papers as well as the review papers and books are available in free PDF download in the document that joins this conference. So I can move very quickly because of lack of time. The construction is done by an isotopy of the traditional way of constructing the Dirac equation, namely by the linearization of the second order Casimir invariant. In this case, we have the iso-Casimir second order invariant, in which this capital G hat is essentially the metric G that we have seen at the beginning, at the very, very beginning of this lecture, multiplied by the iso unit. So this is the object that we have to linearize. Very well. First of all, we have to identify the isospaces underlying the structure. Well, now there are two. First, we have the orbital, the iso-Minkowski, and then we have the isotopic spin, not to confuse with the isotopic spin in nuclear physics. This implies that the total iso unit is the isotensorial product of the orbital and the spin part, which is assumed to have this expression diagonal because it's assumed to be positive, definite in this formulation. Not so for the Lie admissible, where this positive definiteness will be broken. Very well. So again, this is the isometric, which is the original metric multiplied by the iso unit. The invariant we are talking about is this expression in which, after simplification, is basically the conventional expression in which the Lorentz symmetry is replaced by this arbitrary metric G, and the line element is multiplied by the iso unit. Very well. And then it's very easy to do the isotopy of the linearization basically by following step by step. And you end up precisely with this is the general formulation on isospace of the Dirac-Santilli isoequation, which is the only one that is invariant under the action of his own isotopic group that I know. The other one that are around, unfortunately they verify the theorem of catastrophic inconsistency. After eliminating, remember, all the unnecessary element, multiplication by the iso unit and multiplication by its inverse, they eliminate, then you reach this expression, which is generally used in calculation, which is the projection in our Minkowski space-time. And let's examine this expression. First of all, there is an m dash. The first thing that you have to notice that the mass of the conventional Dirac equation is subject to what we call an isorenormalization. It's unavoidable because the speed of light is gone. So it's no longer the universal constant. So mc squared is gone. You have to replace with the local geometric invariant. And this implies automatically an isorenormalization of the mass. This is crucial for the consistency in the representation of the synthesis of the neutron from the hydrogen atom. Remember the inconsistency we discussed on lecture 1A. Inconsistency due to the fact that the rest energy of the neutron is bigger than the sum of the rest energy of the proton and the electron. Therefore, requiring a positive binding energy, which is anathema. For quantum mechanics, the Schrödinger equation blows up, as no longer admits solution. While this intrinsic property of the Minkowski-Santilli isogeometry allows to regain consistency, because in reality the rest energy of the electron becomes so large to allow not only to go back to the presence of the negative binding energy as it should be, because the proton and the electron have opposite charge. So therefore, in the synthesis of the neutron, we must have a negative binding energy of Coulomb nature, of course. So this simple consequence of the geometry has very profound implication, including new clean energies and fuels. But the price to pay, so to say, is surpassing Einstein theory, of course, only under conditions unthinkable during Einstein and not during the conditions set forth by Einstein. Then let's look at the matrices, the gamma hat. They are called the Dirac-Santilli isogamma matrices. Here is their expression, and here is their anti-isotopic commutation rules. Of course, they anti-commute in the isotopic sense, which means by sandwiching the isotopic element in between every product. But look at the right-hand side. You see again the most general possible metric we saw at the beginning. What does this mean? Remember that Schwarzschild is a tiny little particular case of this universal metric. This means that in this equation you can read Schwarzschild directly into the iso-Dirac. But look at the formulation of the iso-Dirac, the way I write them down. I write them down, this is the Pauli-Santilli isometric, but this is its isodual, which means it's anti-Hermitian. Why so? Because I interpreted this as the spin of an isoparticle, and that is the spin for its antiparticle. Namely, there is something very deep here that another aspect another belief of the 20th century that I have never accepted since the time of my graduate schools. I was told that the Dirac gamma matrices characterize spin 1/2. Ladies and gentlemen, I never accepted that statement for the very simple reason that there exists no irreducible or reducible representation of the conventional SU2 spin symmetry, which is 4-dimensional. So therefore, I cannot accept the gamma matrices as representing only one particle. The only consistent representation that I can accept is that it represents a particle and its antiparticle. This implies that the interpretation of the Dirac equation throughout the entire 20th century is not necessarily the final one. Indeed, the isodual theory of antimatter originated precisely here, because in the real formulation by Dirac, here you see -1. It was this -1 that stimulated me to construct a new mathematics, isodual mathematics, and then discover and construct the isodual theory of antimatter from Newton all the way to to quantization or second quantization. We will review this aspect at some future time. Very well. After identifying the isotopy of the Dirac equation, and particularly the Dirac-Santilli isom matrices, then it's very easy to construct the realization of the isotopy of the spinorial covering of the Lorentz-Poincaré symmetry. Here is the explicit expression. Those are the SL2C expressed in terms of isogamma, and this is the case for the rotational and the angular expression and so on. And then it's very easy to see that this realization via the isotopy of Dirac gamma does indeed verify the commutation rules that we had expected from day one. And this essentially completes the study that I did for the isotopy, for all infinitely possible isotopy of the spinorial covering of the Lorentz-Poincaré symmetry. We remain with the discrete transformation. Their lifting under isotopy is so trivial that it's not even worth mentioning. And here you can cancel all the I. This looks like a conventional expression when you project it into our space-time. This is the case for the time inversion or for the space inversion. Very well. Now, but the implications are non-trivial again. It is written everywhere in 20th century particle physics that parity is violated in nature by weak and other interaction. Ladies and gentlemen, I believe that this statement is only due to use of insufficient mathematics. Why so? Because if you use isomathematics, then, as it is the case for the rotation, the Lorentz, the SU2, and other symmetry, parity too is recovered as an absolute exact invariant. How this is done? With isotopy, you can do it in a variety of ways. For instance, this is the case for the PT. This is the PT in a conventional PT. You can reformulate in terms of iso-unitary expression by factoring out the square root of the isotopic element, and then by construction, the isotopic PT is indeed fully invariant. There is the variance for both parity and time reversal verified exactly. And all the parity violating terms are embedded in the isotopic element and the iso-unit. Once you embed all the parity violating terms in the iso unit, then you remove it from the system. They become, and therefore automatically they become an invariance. Alternatively, if you have an expression, an eigenvalue expression such as this one, in which you have a Hamiltonian that is parity conserving and another term that is parity violating, you can identically reformulate it in such a way, with such isotopic form, identical, this is not equivalence, identical in which again the parity violating terms are embedded in the isotopic element. And in conclusion, ladies and gentlemen, the very essence of the isotopy of both the Lorentz Poincaré symmetry as well as of their spinorial covering is to show that they are valid under conditions dramatically broader than what was believed during the 20th century, including the discrete symmetry that they are re-established as being exact. So the rotational symmetry is re-established as being exact for all possible ellipsoidal deformation of the sphere. The Lorentz symmetry is re-established as exact for all possible local variation of the speed of light. The dilation and time reversal, etc. Therefore, this is the very, very essence of the isotopy, namely to maintain the conventional space-time prove that they are valid under much broader condition, and merely introduce broader realization thanks to the prior working out of the adequate mathematics. Because if you use conventional mathematics, you end up with the belief that parity is violated in nature, that rotational symmetry is violated, the Lorentz symmetry is violated in nature, while in reality they are not. Very well, this is the final part of this lecture, namely to give you a few examples of experimental verification of the isotropy of the Lorentz-Poincaré symmetry. I shall indicate that, that the isotropy of the Galilei symmetry and the Lorentz-Poincaré symmetry have now experimental verification in all quantitative branches of science, that is in Newtonian mechanics, in particle physics, nuclear physics, superconductivity, chemistry, biology, astrophysics, cosmology, etc. So I can only give you only a few representative examples, because the topic now covers entire volumes dedicated entirely to experimental verification. Let me go back to the issue of magnetic moments in nuclear physics. This is the position in nuclear physics, namely there is the claim that quantum mechanics is exactly valid. But it happens that magnetic moments are contained in between two minimum and maximum expressions that are called the Schmidt limit. The point persists, however, that quantum mechanics has been unable to achieve an exact numerical representation of the simplest nucleus, the deuterium, because 1% has been missing. And the deviations for bigger nuclei increase with the mass to become very embarrassing when you go to large nuclei such as the zirconium. Ladies and gentlemen, a theory can be claimed to be exact under center conditions when it represents all experimental data. If one of them is not represented, that theory cannot be claimed to be exact in those conditions. Of course, the appropriate broadening, generalization of that theory is and must be the subject of scientific debate. But the denial of its need is corruption and should be denounced as such. And I don't want to be part of that. Very well. So this is the model that I proposed at, when I was at Dubna. There was a meeting on deuterium, and this was the publication in which the article appeared. The exact representation is absolutely elementary. You do it with two lines. Basically, again, what you admit, about 1% deformation of the proton and the neutron caused by their strong interaction. Those interactions are called strong because they are strong. So therefore, it's very logical to expect a deformation of the charge distribution of those particles. Once you deform the charge distribution of a spinning particle, automatically you have a change in the magnetic moment, and therefore it's very easy to do the calculation, and you end up with the actual numerical value of the actual shape of the proton and the neutron, allowing an exact an invariant representation of the magnetic moment of the deuterium. It's also very easy to extend this principle to all nuclei, and achieve an exact numerical representation of the magnetic moment of all nuclei. So all this Schmidt limit are eliminated for an exact representation. But the price to pay is that relativistic quantum mechanics is no longer exactly valid. Because if you consider exactly valid, then this what remains as standing. Very well. Let me go now to give you an idea also of the reconstruction of another exact symmetry that was believed throughout the 20th century as being broken, so-called broken. It's the so-called isospin symmetry in nuclear physics that was believed to be broken by electromagnetic interaction, as well known due to the fact that the proton and the neutrons do not have the same mass. Again, this statement that isospin symmetry is broken in nuclear physics is due to simply to the lack of insufficient mathematics, or mathematics not adequate for the complexity of the problem considered. And in fact, if you use isomathematics, it's very easy to prove that the isospin symmetry for the proton and the neutron remain exact. Despite the difference in masses by the proton and the neutron. The way to do it is elementary. There is a paper here that you'll find in free PDF download in the joining the DOC document, and is the part which I wrote at Estonian Academy of Science, and as one of the many illustrations that we worked out there. And basically what you embed the difference of the mass, you embed it in the iso unit, and you construct then the mass operator in such a way that you get the actual numerical value of the mass of the proton and the mass of the neutron. And you also get the exact value of the charge. So you cannot ask for more. So again, I suggest caution to colleagues to claim violations of fundamental space-time symmetry, in this case is an internal symmetry, before studying in detail isomathematics. Incidentally, the reconstruction of the correct SU2 isospin symmetry for nuclear physics extends also to SU3, that can be reconstructed as being exact at the isotopic level, while maintaining all the beauty of the existing Mendeleev classification of particles into family achieved by the standard model, in which I do believe firmly as being the final classification. That can be reformulated with an exact SU3 symmetry. Very well. Let me pass now to the